Thank you once again for giving me the opportunity to give a presentation here at the Indian Science Day. It's a great honor for me to give this presentation on soot and laser-induced incandescence. My name is Per-Erik Bengtsson and I work at Lund University in Sweden. And down to the right here you can see the building where we do our research, and here you have Sweden, and Lund University is just at the southern edge of the country. So I will talk about soot and laser-induced incandescence, and I will start to do a short introduction. Then I will say some words about soot and how it is formed. Then I will describe some different diagnostic techniques for soot. And after that, I will concentrate on laser-induced incandescence, and I will give some different examples of how we have used laser-induced incandescence to measure on soot particles. And finally, I will give some final comments. Very briefly about our division. We was established in 1991. We are around 60 researchers today, half of them PhD students, and half of these PhD students are from different countries around the world. I'm the head of the division, and at this division we have 15 well-equipped laser laboratories. The main research topics are optical and laser diagnostics and also chemical kinetics. But I would like to say that it's mainly the optical laser diagnostic activity which is extensive. We have for long worked on combustion. That has been our main topic, but we try to broaden our activities, and we also work on gasification, air pollution, entomology, catalysis, plasma processes, sprays, and so on. In combustion, we don't work so much with fossil fuels anymore. It mostly concentrated on hydrogen, ammonia, biomass combustion, metal combustion, and so on. I have a lot of different pictures here, but I will not discuss them today, because today I will focus on soot. When talking about the soot activities at Lund, I think we can divide them into mainly three different parts. One is the fundamental research, where we try to understand soot formation processes. And often we use premixed laminar sooting flames, where we have a burner down here, and by probing different heights here, we can follow how soot is formed and how it grows as a function of height. The second thing is that we develop a lot of laser techniques to probe soot, to measure sizes, concentrations, morphology, optical properties, and so on. Then we also apply the laser techniques to various combustion devices like internal combustion engines, gas turbines, combustors, and so on. Yeah, soot is the focus, and here is an example of a combustion engine that produces a lot of soot and does not think about the efficiency and don't think so much about the pollution. If we take a sample here and look at the soot in a microscope, we will see that we have these chain-like structures, and it can be seen even more evident on this picture. So putting a sample of soot in a microscope with high resolution, then you can actually see all these clusters. And if we pick one of them, soot looks like this, like small, rather spherical monomers or primary particles combine into these long chains. They mainly consist of carbon, and the rest is mainly hydrogen. If we now take a closer look at an even higher magnification, we can see that if we look at young soot, we have a more amorphous soot structure. But if we have older particles which have been sensed higher temperatures, we can often find a more graphitic structure. And so when young soot is formed, it's more amorphous. When it becomes older, it becomes more graphitic. And the important thing here is that more mature soot absorbs much more efficient than young soot. And I will come back to this in a while. Only some few words about soot formation. When we have soot formation, like in a candle flame, first we have the paraffin here that is evaporated. It is broken down into small molecular fragments before the soot is formed here, and we get the growth of polycyclic aromatic hydrocarbons as precursors of soot. Then they collide and stick together and form the first soot particles, and they may have sizes of 1 to 1.5 nanometer. These small particles then grow by surface growth, and they collide and stick together, and as they are pretty much liquid-like in the beginning, they form new, rather spherical particles before they combine and form these long aggregates. And one thing that is important to point out here is that soot formation is not fully understood yet. So that is why we focus a lot of our diagnostics to try to get some more knowledge about soot formation. Another thing that I would like to point out is that we always have oxidation as well in flames. And if we have a well-operating candle flame, as you know, we have no soot that leaves the flame. In a good situation, all the soot is oxidized before it leaves the top of the flame, so we don't get a lot of particles out. Then again, as I said before, if we have the small young particles and compare with the older, more mature particles, there are some differences. The first particles are very small, and they have a low density. So the density becomes higher when they become more mature. They are more liquid-like in the beginning. They become more solid when they get older. So during growth, soot becomes more mature, and that is quite big research nowadays to study maturity of soot. So when soot becomes more mature, the hydrogen content decreases. There is a change from amorphous to graphitic, and the optical properties change. So why I stress this is that this variation in soot properties, that leads to uncertainties in the interpretation of the results from the diagnostic methods. So many of the techniques that we use are based on the absorption properties. And if they are different and we don't know if we probe young or old soot, then we will get some additional uncertainty in our interpretation of the results. So before I start to talk about laser-induced incandescence, I would like to talk about some other different techniques that you can use to study soot. And I think you know most of them already. You can, of course, study the emission from the sooting flames. So emission spectroscopy. We know there is a lot of yellow light coming here. We see that. And that follows the Planck radiation laws. So based on that, we can derive the temperature from a flame like this based on pyrometry. For example, you can detect the signal at different wavelengths, maybe at 2 different wavelengths, and take the ratio and convert that to a temperature. The problem is that you have a poor spatial resolution because you will average the emitted intensity line of sight. So you will only get some kind of an average temperature in the interpretation. But that's very simple. You can look at the emission from a flame. The second technique, which is very much used, is extinction. Extinction is in fact the attenuation when you send a laser beam or some light through a region where you have absorption. You measure the transmitted intensity and relate it to the incident intensity. And if you know the length, we can actually derive the extinction coefficient. And often when you have very small flames, the extinction coefficient is the same as the absorption coefficient, because the scattering contribution can often be considered as negligible. So the extinction is in principle often the same as the absorption. So in this region here, you can then derive the soot volume fraction by measuring the intensities before and after. And you can, you know the length, you know the wavelength that you use. And then you have to put in some value on the E of M, which is the absorption function. It's somehow the absorption efficiency. So if you don't know that value, and often you don't know that value, then you will get some uncertainty when you derive the soot volume fraction. I will come back to the extinction later on when we discuss the LII also. Another technique is laser-induced fluorescence. And the reason for mentioning this technique is that you can easily get absorption by polycyclic aromatic hydrocarbons, which are the precursors of soot. And some examples here are pyrene and anthracene. And they also fluoresce at specific wavelengths. And by combining the detection of the precursors with the soot from LII, then you can get additional information, and I will show an example later on this. The fourth technique is elastic light scattering, which is the elastic scattering that you get if you send in laser light towards soot particles. And that is proportional to 1/λ4, so you get much more signal if you have a short wavelength. You have a function here of the refractive index. So it's a scattering efficiency in this, formula. And here you have the concentration of soot particles, and then you see that there is a very high dependence on the size. The size is, the d is the diameter here. We can combine the elastic light scattering with, for example, LII or with extinction to derive more information about the soot. So now I will come to the technique that is the focus of today, and that is laser-induced incandescence. So the way that we use this technique is that we have soot particles here. We expose that to a laser pulse, and often we use a neodymium YAG laser with a duration of 10 nanoseconds. So the soot particle absorbs this radiation, and we put so much radiation on the particle so we can heat the particle to around 3,500 to 4,000 K. And then at this high temperature, we get much more radiation, much more thermal radiation or blackbody radiation from the particle. And this radiation, this is in fact the LII signal. That is what we would like to detect. But there are other processes going on when we have heated the particle to this temperature. We will, of course, get heat conduction to the surrounding. So when we have this laser heated particle, that will, of course, return to the surrounding temperature if we let that happen, if we don't put more light onto the particle. So that heat conduction term takes the particle back to the surrounding temperature. If we get too high in temperature, we may get sublimation. So some of the material may be sublimed or vaporized. So you see, it's very complex physics behind LII. And we have a heat transfer model that we model the LII signal, how that should look like in time. And that involves all these different terms here. But somehow there are more complex things that may happen. You might get thermal annealing, which means that when you get a higher temperature in the soot, it might be a transfer to more graphitic from the amorphous structure. You may also get photodesorption and oxidation. If you have really advanced heat transfer models, you can add more terms to this equation. Okay, so that was some basic introduction to LII. Now I would like to go through 6 examples of how we use LII in our research. And we will start to talk about LII for particle sizing. And then I will first say a few words about our McKenna burner flame, which is a premixed flat flame. So it's 60 millimeter in diameter, and we have a sintered porous plug down here. And we push an ethylene air mixture through, and at 4 millimeter height, we start to get the first soot particles that are formed, and then they grow as a function of height. And if we then take samples at different heights and study them using transmission electron microscopy, we see that at 6 millimeter, we have rather small particles. At 10 millimeter, we start to get some aggregates, and at 16 millimeter, we have obtained these chain-like structures. What we did in one investigation was that we studied the LII signals at different positions in this flame, and we used this experimental setup. We start to use a neodymium YAG laser at 1064 nanometer. We expand the laser beam and cut out the central part and relay image that into the flame. And the reason for doing this is that we would like to have a top hat spatial profile at the center here. And the reason is that we would like to heat all the particles in the probe volume to the same temperature, so we get no edge effects. Then we have done a 2-color detection here. So we look at the LII signal, we image that onto 2 different photomultipliers. And by having 2 different wavelengths that we look at, we have different interference filters here, we can take the ratio of the signals and we can measure the temperature of the heated particles. And I would also like to point out that it's preferable to use short detection wavelengths because we would like to suppress the background flame luminosity. And so in principle, I mean, it's Planck radiation from the background flame luminosity. It's also Planck radiation that we look at with the LII. So in order to suppress the background flame luminosity, we can make use of the Wien displacement law, which says that when we get higher temperature, the whole spectrum is moved towards shorter wavelengths. So it's in order to get a good background suppression, we should detect at short wavelengths. Then we did some measurements at different heights above burner. And here we see 8 to 16 millimeter height above burner. We see that at low heights, we have a very fast decay. And when we go to higher positions, we see that the decay increases in time. Yeah, we have a longer decay. And how can we explain these signals? Well, small particles cool faster because the heat conduction loss to the surrounding will be faster if you have small particles. So how can we now measure the particles sizes, or how can we interpret these decays to get out some sizes? Well, we take a look at the time result signals. We have detected these 2 signals in time. Since we have these 2 signals, we can take the ratio and convert that to temperature by using the Planck radiation law. If we then, in this equation, introduce the wavelengths, we have the intensity ratios of these 2 signals. We have to make an estimation of the E of M, of the absorption. Normally you put this to 1. Then you can derive the temperature, and for this, these 2 signals we see here, we can derive the temperature as we see down here. So the background flame temperature is around 1550 K. Then we heat the particles up to 3000, maybe 200 K. And then we get a decrease in temperature when the heat conduction loss to the surrounding works. Okay, so now we know the starting temperature here. And when knowing that, we can put that temperature into our simulation. So we can use our heat transfer model to actually produce time-resolved signals theoretically for different particle sizes. Then we take our experimental data and fit to this library of experimental decays. And then we got this result at the 10 millimeter height above burner. We got the result that, 9.8 nanometer. Of course, it's not that accurate, but around 10 nanometer particle size in this flame. And then you can also do this particle sizing in applied environments, for example, in engines and so. But I will not show any results from such measurements here. So that was the first example. Then I go to the second one, and that is a study of soot formation in a high pressure flame that was submitted and accepted by the at the last symposium, which was in Australia as a web conference now in January this year. Okay, so what we do then is that we do two-dimensional imaging of soot volume fraction. So first I show you a very short animation. We have the laser beam. We expand that using a lens system. We produce a laser sheet that cuts through the flame. So we get the laser beam interacting on a two-dimensional surface here. We image that onto the CCD camera, and then we get a two-dimensional image of the LII signal, where we can see that during a 10 nanosecond period, the soot was distributed in a way like this. We had areas with a lot of soot and areas with no soot. So this is an instantaneous image. Once again, we used 1064 nanometer excitation to avoid PAH interference. If we use wavelengths in the visible, there is a risk that we get some polyaromatic hydrocarbon absorption and also fluorescence that may contaminate our LII signals. We suppress the background luminosity using an optical filter that only transmits below 450 nanometer. And here we use a double frame camera. And this double frame camera can take two images very close in time. And if we take one just before the laser pulse, we can get the background signal. And if we take one after the LII's signal, after the laser has interacted, then we get both the LII signal and the background. So then we can automatically subtract the background during a single shot detection. The last thing to mention here on this slide is that when seeing a signal like this, we see a signal and we can say here we have a lot of soot and here we have less soot and here we have no soot. But in order to make an LII signal quantitative, we need some calibration. And that is often done using extinction measurements, as I will show you later. Okay, so what did we do in this study? Well, we studied some different flames at different pressures. And here we have some methane flames, methane diffusion flames. Here is the atmospheric flame. And then we have 5 atmospheres over here. And we see that when we increase the pressure, we will get much more light and also much more soot then. In this measurement, we actually used 532 nanometer as the laser beam wavelength. We have a diode laser here, which we use because we would like to measure the extinction in order to make the LII signal conversion to absolute soot volume fraction. So some results then. When we have very low pulse energy, we only get the fluorescence from the polar aromatic hydrocarbons that can be excited at using the 532 nanometer laser beam. And here we see the half image of the polycyclic aromatic hydrocarbon. And if we look at the polycyclic aromatic hydrocarbon fluorescence as a function of height, we see that we get a signal here. We get a maximum in the PAH fluorescence, and then it decreases again. What we do then is that we increase the pulse energy so much that we get a strong LII signal. And then we get the signal on the right side here. And then we know that the soot volume fraction can be derived from this LII signal. And then we have this red curve here, which shows that the soot volume fraction starts to increase at the same point as where the fluorescence from the polycyclic aromatic hydrocarbons decrease. So PAHs are known to be precursors of soot. They have a maximum, they decrease, and then the soot volume fraction increases. Since we may have some contamination from fluorescence from polycyclic aromatic hydrocarbons to the LII signal, we have to take care of that and subtract that part. It's only a minor effect. So the blue curve here is when we have the contamination from the fluorescence signal, but we could actually subtract that in an adequate way and get only the LII signal here. So in this study, we studied sooting methane diffusion flames. We could see that PAH fluorescence from PAHs precedes the increase in LII signal. And we could also see that soot maturity increases strongly along center line until the position with maximum soot volume fraction. So the soot that is formed first have a lower absorption efficiency than up here where we have the maximum soot volume fraction. Okay, so that was the second topic. Then I have my third topic here, which is an example of how we can measure three-dimensional soot volume fractions. And then we need some advanced lasers and some advanced cameras. In this case, we have a pulse train of 8 pulses coming here. They come very close in time. Each pulse is only around 10 nanoseconds, but all these 8 pulses can be delivered within maybe 500 nanoseconds. And if we have a scanning mirror here, that can scan very fast, which means that the direction of the laser beam can be slightly different out from this mirror. Here we have then some beam shaping optics, which we can produce laser sheets with. So we can produce 8 laser sheets with a very short distance in between, and where we can have a high-speed camera that can take 8 images, where each of these 8 images only measures one of these images. So when we do measurements in this flame region here, we can get a sequence with 8 different images. You can see that they are slightly different, but they are taken within 500 nanoseconds. So from a yeah, from a combustion point of view, on this time scale, nothing happens with the chemistry or with the flow. So we have done some 8 semi-simultaneous measurements. And if we then, okay, you can see we have a high resolution in each of these 2-dimensional images. Then we can combine them to 3-dimensional images with a slightly, well, not so good resolution in the 3rd dimension, but still we can have iso concentration surfaces, here 1 ppm, here 2 ppm, and here 3 ppm of soot in this flame. My 4th work I would like to mention here is where we combined laser-induced incandescence and elastic light scattering for studying the influence of potassium on soot formation. And the motivation for this study is that we know that when we burn biomass, we can have high metal concentrations. And not only potassium, but also others. And we did a study where we actually wanted to see how different metal chlorides influenced soot formation. And in this study, we used the similar type of flame. Up here, we have this premixed flat flames. And what we did was that we took these salts at 3 different concentrations and dissolved in water. And as a reference, we of course had just distilled water. But then we could aspirate these solutions into the burner. And then we did measurements to see how the soot evolved in the flame here for these different metal salts. Here is the experimental setup. What we did was that we used 1064 nanometer for the LII, and we had a beam, a lens system here, so we could make 2-dimensional images in the flame. We used 532 nanometer for the elastic light scattering, and we used extinction for calibration, so we could calibrate the LII signal into absolute soot volume fractions. And here we have some results. From LII, we have measured the soot volume fraction as a function of height above burner. And we can see that when we add potassium chloride, we see that initially there is not a big effect on the soot. But a bit later here, we see that there is a decrease in soot formation. So the soot volume fraction becomes lower when we have a higher concentration of potassium chloride. But from a soot formation point of view, it's even more interesting maybe down here, where there seems to not happen so much. But okay, we will focus on this region now, because from LII, we couldn't see a big difference when we increased the concentration of potassium chloride. But the interesting thing was that when we combined measurements with elastic light scattering, in this case, we see here how much elastic light scattering we get as a function of height above burner for the reference case. We know that the soot volume fraction is the same, but when we add potassium chloride to the reactants, we see that the elastic light scattering goes down strongly. When we add even more, it goes down even more, and also for the last one. So we see that additional potassium chloride clearly decreases the elastic light scattering, but still we have the same soot volume fraction. So how can we explain that? Well, we know that LII is proportional to the volume of particles. The number concentration multiplied by the size raised to the 3rd exponent. Elastic light scattering is proportional to n d6. So if we now take the ratio of these signals, and we simply derive the size from these two equations. Then we see that if we have the same LII signal up here, but we get a lower ELS signal, that should mean that the size decreases when we add potassium. So that is what we can derive from our measurements. What we now also did in these flames was that we actually studied in using transmission electron microscopy how the soot looked in the reference flame from sodium chloride and from potassium chloride. And when looking first at the reference flame, we see that we have an average size of around 17 nanometer. For the sodium chloride, there was in principle no change in the size of the particles. And when I mean size, I mean the primary particle size, not the size of the whole aggregate, just the size of the small monomers here. But for the potassium chloride, we see that these small spheres, they are much smaller. And we get only a size of maybe 13 to 14 nanometer here in comparison with 17 nanometer when we add potassium chloride. So we see that there is an effect of the size when adding potassium. What we thought is interesting now is that we would like to know how potassium chloride addition influences the formation of polycyclic aromatic hydrocarbons, since they are precursors of soot. And we have recently made a follow-up study showing that the concentrations of small PAHs, like 2 rings PAHs, they are not affected by potassium addition. Whereas the concentration of large polyaromatic hydrocarbons like 4 rings, for example, like pyrene, the concentration of them becomes lower. And we have recently submitted this work to Combustion and Flame. So my fifth work I would like to present here is some oxidation studies in engines. In this case, we used 1064 nanometer neodymium YAG laser. We shaped it to a laser sheet, so we have a laser sheet passing through the engine. We also, as we normally do, use the extinction to superimpose, we superimpose the extinction laser on top of the LII laser in order to be able to make quantitative measurements. In this optical engine, you can see here that we have a very strange piston shape. Actually, the top of the piston is not flat. It has this very strange shape. And that you normally have in engines because you would like to have some better mixing. So, but that also gives a lot of problems in the measurements. So I've written here that piston head has curved shape. And the problem with this is that you get a non-homogeneous pulse energy distribution, because when the laser light passes through here, then you get a lot of refraction in these surfaces. And then it's difficult to get, to know exactly what pulse energy or fluence you have at different locations. Another problem when working in engines is that you get a lot of soot contamination on the mainly on the detection window. That is the main problem, because on windows where you send the laser beam through, often you can clean them using the laser, and also on this side. But on the window on this side, there is a big risk that you get contamination of soot. and you have to dismount the engine quite regularly in order to do measurements. And here you can see some results, and that is how the soot concentration change as a function of crank angle degree. So the different numbers here, 25, 30, 35, 40, 45, up to 70, means that the piston is going down. So you can see the piston shape here, and you can see how we have imaged the LII, and you can see that we have soot volume fraction here. So a high soot concentration here, and then this piston goes down, and down here you see that we have a lot of soot in different regions here. And then when looking up here, you can see that the soot concentration goes down. For each time step, you see that the soot concentration decreases. And that is because you have soot oxidation in the engine. So using LII, we could follow the oxidation process in the engine, and we could also then study how the age of the injector influenced the soot formation. And we also tried some different fuel additives to see how they influenced soot formation. And we used a soot reducer that, we could prove that the soot reducer really worked, and we got less soot in the engine during operation. So now to my final example, which is LII measurements in an oxy-fuel test furnace. So this was a measurement campaign that was done in Gothenburg. This is quite a big combustor. It's 4 meters in height, and the inner diameter here is 80 centimeter, and we measured in the red region here. Down here we can see the injector. We have the fuel, which is propane in this case, but we aim to measure, to use biomass in future. But for this test measurements, it was propane. We can then introduce the air either in this as the primary oxidant or as the secondary oxidant. From the measurement point of view, we used in principle the same system as before. We had the neodymium mag laser at 1064 nanometer. But since it was such a big length that we wanted to image onto the detector, we used a very long focal length lens. And the reason is that we don't want the fluence, which is the pulse energy per cross section, that should not change too much over this region. So that is the reason for using a very long focal length lens of 2 meters. We also use the diode laser here at a very long wavelength. It should be above 700 nanometer, because we would like to minimize the scattering contribution, and the longer wavelength you use, you become more safe, that you can actually say that the extinction is the same as the absorption. You can also minimize the polyaromatic hydrocarbon interference, which means that if we use long wavelengths above 700 nanometer, you don't get any absorption by the polyaromatic hydrocarbons. And here I will show you how it looks like. And okay. Now I did some mistake here. Oops. Can you still see the presentation? No?
No.
I don't know what I pushed. Okay.
Yeah.
Can you see? Ah.
Yes.
Okay. Yeah, I would like to show some single shots here. So this is what it looks like inside the combustor. We can actually see that from shot to shot, we have a big variation of the soot. So we see it's highly turbulent, and we have regions with very high concentrations as well as we have soot-free regions. And if we now take a look at a small region here, and we look at 1,000 single shots, we can see that we have a maximum concentration of around 1 ppm. But we also have regions, well, in 54% of the cases, we have actually no soot in this region. So if we had averaged 1,000 single shots, we had as a result got a very low average concentration. But since we detected on a single shot basis, we can actually see the fluctuations, and that is very important if you would like to compare with soot models. So I think in some cases it's really necessary that you collect the single shots. So finally, I will just point out some problems that you can realize when you do LII in large facilities, and I've shown you some examples. One is that you might get problems with the windows because soot attaches to the windows, and also additives like metals attaches to windows. For example, potassium can build up on windows. Another thing you have to think about is that there is a variation of the laser fluence along the laser beam, and that may give you a problem. So an advice is to use a very long focal length lens when you focus your laser beam. And in order to get quantitative measurements, you need to calibrate the LII. And the method that we often use is, as I've shown you, to do semi-simultaneous extinction measurements, where you overlap the extinction laser beam with the LII laser beam. Another thing to think about is that there is an uncertainty in the optical properties of soot. So small incipient soot particles, young soot particles, they absorb less than mature soot. And LII has a limited sensitivity to incipient soot because when you heat the mature soot particles up to 3,500 K, the young soot particles are only heated to much lower temperatures. And then since the Planck radiation has a T4 dependence, then one realizes that there is a low sensitivity to the small incipient young particles. Another thing that may happen is that you may get beam steering and beam inhomogeneities. That can be from refraction in glass windows. It can be from density gradients. And also, it's very difficult to measure if you have a lot of soot. If it's so optically dense that it's difficult to get the laser passing through the flame that you study. So you can get a lot of absorption by soot along the detector path, but also from the interaction region to the detector. So yeah, so there is a limitation to LII in that case. My final comments is that soot is a very interesting material. It's very complex, and that the characteristic properties varies largely with maturity. And if we have limited knowledge on the soot characteristic properties, for example, the optical properties, that limits the accuracy we have in our laser diagnostic techniques. Laser diagnostics can be very good. We can measure non-intrusively in many cases, and also with high temporal and spatial resolution. But often we have to face some limitations, unfortunately. And I think also it's very important that we think about combining different diagnostic techniques. It can be various optical techniques that I have shown you here, but it can also be to combine optical techniques with sampling and detection using external instruments also. And finally, I would like to thank the financing agents for being allowed to do this work, and also my Soot group that are working right now, and also previous colleagues I've had. But my Soot group right now is Kwong Lee, who is assistant lecturer at our university, and my three students, Sandra, working with laser diagnostics of soot towards environmental applications. She will graduate this year. Also Manu Manari, he's actually from the Kerala region. He will defend his thesis also this year. He also works with laser diagnostics of soot, more towards engine applications. And finally, Saga Bergqvist, and she works with laser diagnostics of soot towards flame investigations. And then I would like to thank you so much for your attention. Thank you.